Gonna turn this over to you. Thank you so much for being here, Marco.
Sure. Yeah, good thing is my voice is all right, so hopefully it'll only bother me. Yeah, I wanted to talk about this open source project we released in November, PG Lake. Is d different ways of describing it. I actually kind of like Postgres for the Lakehouse. It's nice and short. So about me, I've worked on Postgres extensions for the last 12 years. First at Citus Data, I led the development of the Citus extension and also developed some other extensions like PG cron. And we were acquired by Microsoft in 2019, and then we continued developing Citus. It became a bunch of different products. And we also developed some other new
Generation.
extensions
Before I
like
start, some background about myself. I did my PhD from UC
I'll
Santa
fix that.
Barbara.
One second.
I did the postdoc at UGA.
um, so we also started some other new extensions like PG Document DB. But in 2024, me and two longtime colleagues, we decided to hop over to Crunchy Data because we were starting to see some interesting trends in the data space, in the analytics space around Iceberg, around DuckDB, and we kind of started forming the ideas that are now kind of PG Lake. And in June last year, we got acquired by Snowflake, so we're now continuing development there and actually open sourced it as PG Lake. Um, and we're also treating this as kind of a building block for connecting Postgres with Snowflake and your wider data infrastructure. So what is PG Lake? So PG Lake is actually a set of open source Postgres extensions, not just one. We sort of modularized it a bit in the same way that, for example, PostGIS is actually a set of extensions. And it lets you query, import, and export raw data files like CSV, JSON, Parquet in object storage directly from Postgres using standard SQL commands like copy, create table. And then it also lets you manage Iceberg tables directly in Postgres. And so this introduces a new storage format in Postgres, essentially, where you can store data in a way that's optimized for analytics and can be shared with other systems as well in an efficient way. And so by using these things, you can run very fast analytical queries in Postgres, where queries are fully or partially delegated into DuckDB, which can do it much faster in many cases. And you can use Postgres almost as a kind of data control plane where you build these data pipelines simply using transactions and SQL, maybe sometimes stored procedures and pgcron and those types of tools. And we found this actually a kind of quite nice pattern for simplifying all sorts of data movement operations. So it's available on GitHub under Apache 2, so you can pretty much do whatever you want with it. Um, so it's not a new project. As I said, we started at Crunchy Data in January 2024. And then pretty quickly in April, we launched a first product with this technology called Crunchy Bridge for Analytics. It was basically taking the Crunchy Data Managed Service and adding the ability to interact with data lakes, with object storage. Then after that, we added the Iceberg implementation. We also kind of started doing a little bit more on-prem. So in November, we relaunched it as Crunchy Data Warehouse. But then, yeah, we didn't get to go on that journey for a long time. So in June, we were acquired by Snowflake. Now, we didn't feel like, there was a need for another warehouse at Snowflake. Snowflake is a pretty good warehouse. But the extensions we built were quite useful in the Snowflake context. And so after some soul searching, we decided, oh, actually, this should be open source, and this is going to be a building block for a lot of kind of our Snowflake Postgres infrastructure. Because Snowflake now has a managed Postgres service that's in public preview that's based on Crunchy Bridge. So why PG Lake? So here's some hot takes, but like Postgres has mostly conquered the operational database world, I would say. It's kind of the default database at this point. If you're building an application, you need to store some records. You probably just use Postgres. At least I imagine in this group you use Postgres. But there's this whole other database world, the analytical database world with, the Snowflakes and the Databricks and ClickHouse and DuckDB and Vertica and other systems where Postgres is relatively disconnected. And it's often like if you read papers from this space, it's often everyone likes to compare against Postgres because you're always going to be faster than Postgres. Because like if you run analytical queries on Postgres and maybe you've done it before in MySQL and you say, oh, Postgres is faster, but like the state of the art analytics databases, they are orders of magnitude faster on the same hardware than Postgres for analytical type queries. And we'll get a bit into why. Um, and then at the in the corner you can see sort of result from ClickBench, which is a quite popular analytics benchmark right now, where well at least the claim is like DuckDB is 400 times faster than Postgres on the same hardware. I think this is Postgres just with default settings, but it is actually a staggering difference. And then also the experience of working with files in object storage with data lakes in Postgres is, I would say, pretty terrible. Like there's just nothing that lets you do that. And that means that you need to use external tools that need to run somewhere that you need to monitor to make sure they're still running that might, and they kind of um, do things in a way where you maybe if you have a failure, you miss data or you have duplicate data. So you need to kind of take care of that as well. So it's actually really hard to just get a CSV file from S3 into Postgres. You probably just download the file, inspect the headers, and look at what kind of ginormous create table statement you need to write, and then you go and do that. But still, despite not being very good at it, Postgres is widely used for analytics. And part of it is, once you start building your application on Postgres and you start collecting all sorts of data, maybe you want to build an internal dashboard. Maybe you want to kind of give your customers a dashboard. And it's just so much easier to still build that on Postgres than to build some whole kind of ETL pipeline. So people use it for Postgres, use Postgres for analytics, but it's not always like at some point it just becomes very slow because also each query takes up a lot of resources and it slows down the other queries. But luckily we can get out of this problem because Postgres is extensible. So anything that Postgres is not good at, we can ultimately make it good at. So like the database world is traditionally divided in these two sort of factions. There's the OLTP faction and there's the OLAP faction. And they don't really talk to each other very much, but there's a few things they agree on, like you should use SQL, you should use transactions, but OLTP databases are kind of operational systems of record. They should support a high rate of queries, tens of thousands, hundreds of thousands, but the queries are very small, usually like insert a single row or look up 10 rows or and then the response time of that is ideally like a millisecond. Where with an analytics database, they're not optimized for query throughput at all. What they're optimized for is for a single query to scan through large amounts of data. And often you're combining data from different sources, so you can have quite complex queries, lots of joins, lots of CTEs and unions, some cleanup that you might have to do of the data. And so it's all about making those individual queries fast. And one of the sort of defining characteristics in terms of the architecture of an OLTP versus OLAP database is row-oriented storage, which is what OLTP databases like Postgres use, and column-oriented storage, which is what analytics databases use. So with row-oriented storage, you store the data like first row, second row, third row, and then there's an index for looking up the rows. And so this is actually very fast for if you want to retrieve a row by an identifier, you just walk the index and there on story in disk, you find the row or in memory, ideally. Now, with analytics databases, this is usually not the type of query you're trying to answer. You're trying to do aggregations across large amounts of data. And maybe there's many different types of aggregations that use different combinations of columns. And it's actually useful to split the data by column. So you get a bunch of values from the first column, a bunch of values from the second column on disk. And that makes projections quite fast. It also means that the data can be compressed really well because some columns, maybe they mostly contain like ones or zeros, and like it just compresses really well. And that's often worth doing because then you can keep more data in memory. But I would say the storage is actually not what makes the huge performance difference for these systems. Like the thing with let's say the Postgres query engine with or operational database query engine. So you look up a row and then you need to do some processing on that row to answer the SQL query. So maybe the query has a bunch of filters, some projections, and each expression, each function call, each operator is essentially a function call internally. And so we call a function, we go up and down the stack. Maybe the function does some allocations and some other stuff, some initialization. And then we go to the next function and we go up and down the stack, the third function up and down the stack. And then when we're done, we go to the next row and we do it all again. And there's a ton of CPU instructions associated simply with like calling these functions. But also it makes very poor use of kind of modern CPU features when you're doing this. So conversely, like in an analytics database, at least the modern ones, they have this concept called vectorized execution, where essentially the query engine takes a vector, an array of values, and every function and every operator is essentially implemented as a loop on a vector. So add two vectors or apply a filter to a vector, and maybe the resulting vector is then a vector of indices, which you can use to select from another vector. So everything is done not on a row level or value level, but on a vector level. And what's nice about that, at least for analytics performance, is that, well, A, when you're processing this vector, it probably just sits in your CPU cache entirely. You don't switch between functions that often, so you don't have all this extra CPU instructions. When you're doing simple enough things, your CPU might have some like instructions that can process lots of values at the same time, these SIMD instructions. And then also modern CPUs have this notion of pipelining where like the CPU internally is almost a little bit like a network where if you in a network, you send a packet and you wait for the response and then you send the next one. That's very slow. You want to send lots of packets and then get some responses. And CPUs are almost a bit like that, where you send lots of instructions into the internal processing units. And then sometimes it might be that some of these instructions are actually jumps and then they jump to some other part of the code and then the pipelining cannot continue. But for vectorized execution, this pipelining works really well. And so if you combine all those things together, that's where you get the sort of crazy, like same hardware does 100 times faster analytical queries than Postgres. So then the question is, can we bring this actually into Postgres? And like in the last few years, we've seen the sort of arrival of good open source uh, analytics databases that can be integrated into other systems. And I think most notably DuckDB. And DuckDB there's some others like Data Fusion, but DuckDB is basically architected like SQLite. So it's like an embedded database system that runs in another program. Like it can be a Python program, can be a dashboard, can be Postgres. And then, it's open source, MIT licensed, and it's also extensible, just like Postgres. So what we can do is basically take Postgres and DuckDB and essentially create a layer of extensions in between to kind of wire them together in a way. And also DuckDB has a lot of features that you kind of want from a user experience perspective in an analytics database, such as making it very easy to work with CSV files, for example, in object storage or some random URL. And so it'd be nice to also bring those things into Postgres. So, uh, so Postgres extensibility is it has a few different forms. Often, many extensions just add some functions, some types, but you can essentially take over Postgres as an extension because there are all these hooks where like points in the Postgres code where it processes, let's say, a DDL command or a query where an extension is allowed to take over. And the extension probably shouldn't break all of Postgres. It should just sort of check, hey, is this command relevant to me? If not, go back to regular Postgres. If it is, then I do something special. And you can also look into much more fine-grained parts of like query planning, where you say, oh, this particular um, type of plan node, we generate it in a little bit of a different way when the extension gets involved. So it gives you a lot of flexibility to essentially extend the user experience of Postgres. And given that we've done this stuff for a while, we've also um, sort of take a little bit more of a liberal view of these hooks, where we don't always necessarily use them exactly the way they were intended, but still in a way where it actually enhances the user experience quite a bit. So in terms of architecture, like we took a bunch of counterintuitive decisions, I would say, when we developed PG Lake. And the first counterintuitive decision we took is that we de-embedded DuckDB. So DuckDB is like SQLite. You run it in a process as part of another program in a process. It's an in-process database, actually. And it has a C API, or I mean, all of its other APIs are just wrappers around the C API. Postgres is written in C. It's really very straightforward to embed DuckDB and just call it C APIs. The problem is Postgres is a multi-process architecture, and every connection to Postgres creates a new process. And so if all those processes are all going to have their own DuckDB instances that all want to, let's say, take 80% of memory and have their own buffer pools, their own thread pools, we didn't think that would be a good model. And there's also the problem that Postgres isn't really very suitable for having sort of these complex multi-threaded dependencies within it. Because, for example, it does signal handling in a way that's not entirely thread safe, and it's has its own specific way of doing memory allocation and error handling that's not always very compatible with, let's say, C++, what DuckDB is written in. So we actually created a server for DuckDB that just runs alongside Postgres on the same machine. So it doesn't really have a network protocol as in TCP, or I mean, we could add that, but it doesn't have it at the moment. It just uses Unix domain sockets. But still, we needed a protocol to talk to DuckDB as well. And I would say this is also a little bit counterintuitive, but we decided to use the Postgres protocol. So Postgres is talking to this local server using the Postgres protocol. And the reason is that then we could in Postgres in the extensions use libpq, which is a very kind of robust, mature Postgres client library that we're familiar with because Citus depends on it a lot. But it's very good at doing the types of asynchronous execution that we need for talking to this server. And also, like the fact that we can talk Postgres to it means we can just connect to the pgdoc server using PSQL, which is very nice for development, very nice for testing. We can run similar automated tests on Postgres and on pgdoc server. So this was a kind of a nice feature. And it also makes it easy to interact with the system. You can actually just connect to this thing. So the pgdoc server has a file cache. So we kind of quite aggressively try to cache files that we get from object storage and also that we write into object storage. And we use just the DuckDB credentials features that it has for storing your Amazon access key ID and that kind of stuff. And then Postgres has its own disk where it stores any kind of metadata that or and its regular Postgres tables. I saw some chat come by. Were there questions or? All right. Um, so what we've done with this architecture is extend some of the regular Postgres DDL commands um, and with sort of new flags or new syntax. So, for example, when you have PG Lake installed, you can create a table which directly from a file. So you basically just say create table with load from. This will go and figure out what this file looks like. It'll try to infer the column names from the CSV header and the column types by just looking at the data, and it'll fill that in for you. So you don't have to tell it like, hey, this is what's in the CSV file up front. And so this makes it really easy to import a file into Postgres and then start doing other things with it. You can also just ask it to just take the columns from the file such that you can then, if you have multiple files to load, that's often a bit more natural. So you can use copy to load CSV, load new line delimited JSON, Parquet. It actually also supports sort of GDAL formats, so you can do shape files and geodatabase and other things. Um, and you can also create a foreign table. And so this doesn't store the data in a Postgres table, so it doesn't take up any storage space. And another nice thing about the foreign tables is that when you query them, the query will get accelerated by DuckDB. Now this works best for Parquet files, for CSV and for JSON, or especially for like zip files or shape files. It doesn't work. Like the queries will still have a lot of overhead because of the parsing. But for Parquet files, this can already be many, many times faster than loading the data into Postgres. But there's still some other cases where maybe you want to get it into a Postgres table because, for example, if you're dealing with spatial data, you often want to have spatial indexes, and for that, you need to get it into Postgres. And then finally, you can copy a query result back into object storage. And so this is very nice because then you can build these whole pipelines where you consume data from one application, do some processing on it, and push it into another application, or you do archival this way, or you can do lots of other scenarios once you can write into S3. And of course, you can also all script this in PLPG SQL functions or in your application. So, but these are still kind of dealing with raw files. It's not always convenient to deal with raw files. It's nicer to deal with tables. So we wanted a way to store tables in a way that's optimized for analytics. So we first thought, okay, maybe we can store like just the tables in DuckDB because DuckDB has its own native file format and it's really fast, even faster than Parquet. The problem is that this will not get replicated, and we always are kind of working on like managed Postgres services where replication is a very core concept where you have failover, where you have backups, or even if you like upgrade a machine that might actually be switching over to a replica. So then you would lose those files, and so that wasn't an option. Another option could we implement the storage format in the Postgres buffer manager? I mean, we've done this before with Citus columnar, and in principle, it can work. You could do columnar storage in Postgres's buffer manager and write-ahead log, so then it does get replicated. The problem is nothing about Postgres is optimized for analytics, including the buffer manager. So the buffer manager is not threat safe. It uses all these tiny 8 kilobyte pages with locks, and it would be very, very hard to make this perform well. And so the other option was, well, we don't store it in Postgres on the Postgres server. We store the data in object storage, which is a little bit slow. So we add a cache, which can be on, let's say, an NVMe drive, which are very fast. And then we only store some metadata in Postgres. And so that can just get replicated. So the primary knows where the data lives in object storage, and the secondary also knows that it can talk to the same object storage. And this is pretty much exactly what Iceberg does. So Iceberg is a way of storing a table in object storage with support for updates and schema changes and partitioning. And essentially, Iceberg is still just a collection of Parquet files, so these columnar storage files with compression, but then with another layer of metadata files, which describe the set of files that are currently part of the table, some statistics on those files. And then there's this metadata file, which contains the current version of the table and its schema and other properties. And everything is immutable. So whenever a table changes, you write new data files, new metadata files. And so to actually read from an iceberg table, you need to know the location, the current location of the latest metadata file. And that information is usually kept in what's called a catalog. And the catalog is essentially just a database that has a table with a record that is a URL. And in our case, well, since we're doing this in Postgres, we don't really need a separate catalog. We can just use a Postgres table as the catalog. And what's nice about using a Postgres table is that you can then actually have transactions across Postgres tables and Iceberg tables or multiple Iceberg tables, because these are the commit ultimately is just sort of writing into a local catalog table. And there's actually a lot of things required for making this work smoothly. For example, Postgres has all these crazy things like sub transactions that can roll back. And then if we generated some files in the sub transaction, we need to clean those up. But we did all that. So pretty much everything that you're used to in Postgres works with these tables like DML, DDL, sequences, default expressions, geometry type works. The only thing it doesn't, I mean, there's a few type limitations around, let's say, very large numerics, and you cannot have a primary key or exclusion constraint or things like that. And so with that, you can just connect to your Postgres instance and create a table using Iceberg. Now, we're cheating a little bit here because we there's this notion of table access methods in Postgres, which have a very nice user experience. You just say using heap or using columnar or and then everything works as it usually does. And then, but the internal APIs for table access methods aren't really suitable for this type of a storage. Like, for example, it requires you to be able to look up a row by its CTID, and there's no CTID concept in Iceberg. So what we actually do is we kind of overload the syntax a little bit and create a foreign table underneath, because the foreign table APIs are much closer to what we need for Iceberg. But the experience is actually much closer to how you would use a table access method, because you can also do create table as select or do DDL commands on this table. Like Postgres is really managing this table. So it's not so much a foreign table from the user perspective.
Ya sizin rahatsız olduğunuz niye de ama 4 kişi gelmişsiniz oraya olmasın.
Eric, I cannot.
Yeah, looking for the mute button.
All right. Cool. And so once you've created a table, you can just treat it like a Postgres table. You can do inserts, you can do updates. If you do update, lots of things will happen. Like it'll scan the Parquet files that are part of the Iceberg table. It'll generate like the updated rows and put them into a new Parquet file. It will generate another Parquet file which contains the rows that have been deleted from the original Parquet file. And then it'll write the metadata files and update the catalog. And so you can have multiple updates in the same transaction or like do other stuff in the same transaction. And then when you query the table, under the covers, it'll actually using DuckDB like scan the Parquet files and filter out the deleted Parquet files. So there's a little bit of like bloat in Iceberg as well, something we're sort of familiar with from Postgres. And so there's also a vacuum process. So every 10 minutes, actually, there's a background worker that runs that will go and look for example, very small files and compact them together, or look for files that have been mostly deleted and sort of compact those together as well. And also, if you're just doing a large update, it'll just rewrite the files immediately. Now, we spent quite a bit of time on making the query planner work quite nicely, like perform well, but also always give correct results that are consistent with how Postgres would answer the query. And I sometimes think a bit of like as what we do as sort of inflating a balloon to find like the biggest section of the query that we can delegate. And actually, we always start with looking at the whole query. So if the whole query can be handled by DuckDB, we just send it to DuckDB. But if not the whole query can be delegated, we look for the sort of biggest subquery that can be delegated. So maybe if we start by looking at the table scan, which includes like the where clause and the projection clause. And sometimes we actually split the where clause, where some filters happen in DuckDB, some happen in Postgres. But if everything can be handled by DuckDB, we kind of look at the next layer of the query, like can the group by be handled? If yes, can the order by be handled? Yes, okay, but not the whole, not the CTE scan, not the outer query. So we then get a Postgres query plan that's partly DuckDB and partly Postgres. So the top node here would be maybe a CTE scan, and then its child node would be a foreign scan that does the CTE. And this way we can support any Postgres query and we get as fast as possible. And there's actually a little bit more to it than that as well, because so we also rewrite certain expressions from the Postgres version of the expression to the DuckDB version. Like a lot of the time, like DuckDB follows the Postgres syntax and mostly tries to implement the same functions. But sometimes the function just does end up having a different name, or it has the same name, but it actually behaves a little bit differently. Um, and so we go through every individual function and operator and kind of test it and see whether the behavior is consistent. And if so, we kind of consider it to be push downable, we call it, but like we can it doesn't block the delegation of the query. But then also, if a function doesn't have a DuckDB equivalent, we can actually sometimes rewrite it. So, for example, to_char will become strf time, and that's actually a big transformation because also the arguments change. And in some cases, we can actually add new functions to DuckDB via DuckDB extensions if they're not in vanilla DuckDB. So this way we can sort of expand the set of things that we can delegate into DuckDB, which makes again the performance better. And also, if DuckDB cannot handle something, it sort of the performance degrades more gracefully. It doesn't become like, oh, this doesn't work in DuckDB, so we do everything in Postgres and super slow, which you'll find in some other extensions. Um, so these benchmark numbers are a bit old, but we've done some comparisons on like ClickBench, just using Postgres tables versus Iceberg tables. And ClickBench it's a fairly simple analytical benchmark where this vectorized execution works really well. So it was more. I haven't done the math, but like it's more than 50 times faster on the Iceberg tables. And so this is actually identical hardware, identical software, same instance, just different table types. And for TPCH, we've done quite a bit of tuning of Postgres to make Postgres go fast, but still like using Iceberg, it's more than 10 times, something like 14 times on average faster. Now, what's interesting is that this combination of Postgres and kind of data lakes and fast analytical performance or fast data transformation performance. Um, I mentioned it earlier, but like it turns Postgres into more of a control plane for data, where you can build these relatively simple, um, like build quite sophisticated pipelines in a relatively simple way. For example, if like when we're dealing with an Iceberg table, because if we insert something, we need to generate new files, upload them to S3. That takes like at least hundreds of milliseconds, so it's very slow. But if we wanted to do just low latency, high throughput inserts, we can create a Postgres table, insert into that, and then periodically delete from the Postgres table and insert into the Iceberg table. Or we can sort of build up say the last 7 days in Postgres, but we also sort of incrementally copy the data over into Iceberg. And because we have these transactions, this is really quite straightforward where we just say, okay, delete and insert. Because if you didn't have transactions for stuff that lives in object storage, like, maybe you managed to write the file and then fail, for example, or like there's all sorts of ways where you could get data arriving multiple times, getting duplicated, or data gets missing. But with transactions, you don't really have that issue. Another thing we've seen quite a bit is where people use pglake to import files that show up in S3 that are being produced by other systems, or in some cases even Postgres itself. But like, let's say you have logs in new line delimited JSON format, or in TSV or in CSV format. So what you can do is you can create a logs table that points to a wildcard sort of file pattern. So then it includes all the files that match the pattern. And you can also ask it to include the file name in the output. And then let's say maybe we want to get this data into a Postgres table, or we want to get it into an Iceberg table. But basically, we want to take all the current files, do some transformation on them, and put them into this table. But also, whenever a new file shows up, we also want to process that file. And we want to make sure we never skip any file or duplicate any file. And so we created this tool called PG incremental that has a few different ways of processing data incrementally in Postgres. And one of the ways is like looking at his list of files as new files show up in this that match the wildcard. We run this insert into select command, or you can specify what command you'd like. But so basically, this is only going to read the new files and it inserts them into the target table. And if it's Iceberg, it actually does it very efficiently because it doesn't even go through Postgres. And so that's a kind of a nice data loading pattern because again, this is sort of fire and forget. You just create this job and it'll run every minute. It'll check whether there's new files and they'll get automatically loaded. So I'll do a short demo using my terminal on PSQL. I I was feeling very well today, so I didn't come up with a very good demo, but I want to just show you a few different, a few of the features we've discussed. So, for example, you can now with PG Lake very easily create a table from a file, and this is actually a compressed new line delimited JSON file. And I don't specify column names or column types, but it'll just go and figure that out for me. And there's actually a bunch of nested JSON in these files. But let's see. So okay, yeah, this is my table. And for example, I could see that in the hour that I loaded, there was one push event in the PG Lake repo. I could maybe load another one, load another hour of data into this table and see that now I have two push events. And so you can quite easily imagine of like, oh, okay, I mean, this is not object storage, so I cannot list the files in here, but I could quite easily write a script that in a sort of transaction loads files from this data source into this table. And the other thing we can do is, let's say we create an iceberg table. If I can get my syntax right. So here I'm creating a very simple events table. And if I insert, let's just do it from scratch, into events iceberg event type. I had a banner sitting over my terminal. Did I name it something else? Oh, I used a JSON column. Okay. Yes. So you can see that actually this takes like 1 second to do an insert, so that's not very nice. So what we can do instead is create this events queue. And so now I have another table that includes all the columns, and I can, instead of inserting into the events iceberg table, I can insert it to the events queue. That's fast because it usually is fast. And now I can set up a job that every 5 seconds takes data from the queue and puts it into iceberg. So now I still have the here. Okay, so now it just flushed. So now it's, now I have my second event, and I can just keep inserting new records. And then I guess it'll at some point show up. Oh, there it is already. So now I actually have this analytics optimized table that's stored in object storage and that other systems can actually access because it's just like if they talk to Postgres to get this URL, they can just directly read from the iceberg tables from object storage. And then I can insert into this really quickly via Postgres. And so that's a nice thing that happens if you essentially glue these systems together. And also finally, in terms of performance, so I have the ClickBench Parquet file. It has about 100 million rows. So you can see I can scan these pretty quickly. And let's say I do some analytical query on here, takes a few hundred milliseconds. And then I've also already loaded this data into Postgres. And I don't know if I want to wait for this query to finish, but it'll usually take, well, it's not crazy bad. It's like 20 to 30 seconds usually, but like just sort of same database, same data, same hardware. You get tremendous performance difference by using like Postgres table versus Parquet or Iceberg. All right, 27 seconds, not bad. All right, so then I go back here. So in summary, yeah, PG Lake is an extension to connect Postgres directly to your data lake. And this architecture, especially with Iceberg, where you can sort of use it as a data warehouse, but also the data is stored in this open format that other tools can also access. That's often what's called Lakehouse. And so you can use Iceberg pretty much as a native table, like all the Postgres features just work. And it is already used in production because we have a whole bunch of Crunchy Data Warehouse customers running this in production. I would say it's cleverly architected, like to kind of deal with some of the actual challenges in practice of combining these two systems. It's pretty fast, and I would say it's easy to use. I think the setup, like currently, especially, you need to sort of compile it yourself. So the setup can be a little bit easier, I think, still. But definitely once you have it running, then it's pretty easy to use. And of course, we're bringing this into Snowflake Postgres and also building more things on top in Snowflake Postgres. And yeah, we've had a lot of great response. And if you run into issues, just let us know on GitHub. If you like it, please give it a star. And with that, I'll turn it over to questions.
Hey Marco, there's some really good questions in the chat, and I was thinking if you want to answer those first, and we'll keep those in the recording, and then if we have time left over, I'll stop the recording if people want to chat, like with voice questions. So if you want to start at the top, that looks to me like the first question is about the architecture. Um, like if you can separate PG server from the Lake server.
Right. Yeah, that's a good question. So can you, right now you cannot separate the PGDoc server from the Lake server. They are on the same machine, correct? Yes, that is correct. So I mean, but mostly it's like, just having it on the same machine is actually pretty nice because, you have very low latency, high bandwidth. We have considered the idea of like, hey, could this live on a different machine? And then maybe you could have like a tiny Postgres server, but still have like a separate thing that has a lot of cores that can scale up more quickly. We've not had a need for that so far. But yeah, I mean, it wouldn't be a huge architectural shift. It will just be switching to TCP instead of Unix domain socket and adding some authentication probably. Um, so next question is difference between using it and PG Mooncake. So PG Mooncake has a lot of similar goals. I think it started like essentially like when we built Crunchy Data Open Data Warehouse, which was still kind of closed source, and PG Mooncake kind of became an open source version of that. Though I think it never really reached maturity. It does, run DuckDB in every process and those kind of things. And I haven't seen any commits on the repo for the last 3 months. So I think I mean, it got acquired by Databricks. I don't know if they're still investing in it. But yeah, I would say the big difference is that PG Lake is a very mature solution where all the Postgres features actually work, and the um, this sort of graceful degradation of performance when something cannot be handled by DuckDB is, we've spent a lot of time on that. I don't think that's MPG Mooncake. Um, so can I achieve the same with JDBC catalog where I can store metadata in Postgres only? So yeah, basically we act like a JDBC catalog. So if you create an Iceberg table in Postgres using PG Lake, then you can connect any Iceberg client that supports the JDBC sort of format to PG Lake. The only thing is that you cannot write to those tables using those drivers. So currently it's read only. Um, are you using Duck Lake for your Iceberg table catalog? So, well, Duck Lake showed up more recently. And interestingly, like before we actually implemented Iceberg, we had a sort of like pre you know predecessor which we used mostly for development, which was very much like Duck Lake because we were just keeping the all the metadata in Postgres. And so Duck Lake is basically it's like Iceberg, but instead of having extra metadata files in object storage, all that metadata lives in the catalog, like in a Postgres database. And I mean, when you use Duck Lake, you kind of have DuckDB as your front end, and then you also need Postgres as your back end. And then this is almost the inverse, where you have Postgres as your front end and you have DuckDB as your back end. So if you like Postgres, using Postgres more, then probably PG Lake is nicer. And if you like using DuckDB more, then maybe Duck Lake is nicer. But we're not using it directly. Maybe we can add it in the future. What sort of performance do you get if you do a single ID lookup? So like these analytics databases, they do use a lot of chunking and statistics on the chunks. So each chunk will typically have a min and a max value associated with it in some statistics. And so then it really depends, is the data sorted by the ID such that each chunk is like a different set of IDs and I can know which chunk to use, or are all the IDs random and they're just spread all over and all the min max values are all just like the entire range. And so it really depends a lot on the storage layout whether a single ID lookup is fast. If it's in a single chunk, it's still under 100 milliseconds. You shouldn't expect it to. I mean, it can actually be 10 milliseconds. It cannot be 1 millisecond. That'll probably never happen. But if it's just anywhere, it can still take hundreds or milliseconds, or if you're dealing with seriously large data sets, maybe still seconds. But it depends on the storage layout. Can you access DuckDB directly? Yeah, that's sort of an interesting thing where if I connect to the pgduck server, so now I'm connected to actually, well, code it just says duckpg, but like pgduck server. And see, some of pSQL doesn't work now because like those tables that \d looks for don't exist. But let's say I can now do well, this I can do with PG Lake, but let's say this is pure DuckDB. And so yeah, so when I talk to this pgduck server, I'm just running the queries directly on DuckDB. Let's see, and yeah, so there's a question of like, can we go through the pre-installation steps? Very good question. I think that's the part where there's currently a little bit more friction because you need to compile the extension. The problem with doing that in a demo is that because it also compiles DuckDB, it takes about 30 minutes or on many computers, maybe 10 minutes on a Mac, but so it's a bit hard to do as a demo. But yeah, I think Elizabeth added a link to a talk, and yeah, there are our docs describe step by step how to set up the extension. So in the GitHub repo, there's a docs folder that has all the documentation.
There is
Um,
also a Docker. Let me get the link. I know there's a separate repo that has a Docker image.
yeah, I think it actually lives in the same repo. That's the easiest way to get started. So you can Like the Docker image will do the full build, and so just in the PG Lake repo, and you can run it just in a single step.
I think the actual fully built Docker image is a different repo, right? Because you still have to build it.
Okay, yeah, the fully built one. Yes, if you can share that. So is the Postgres Iceberg table catalog accessible to external query processors via REST API? So so we've been adding REST support. That's kind of one of the things we started doing the last few months. And so currently, and we sort of still consider this to be experimental because it raises some questions around transaction consistency. But so we can now use external REST catalogs. So if you're using Polaris or Snowflake or something that runs outside of Postgres and has a REST API, we can actually create tables via that catalog or consume tables that are in that catalog. We've done experiments in the past where we actually expose a REST API for the PG Lake tables by essentially hacking ourselves into the database schema of a REST catalog like Polaris. So we've done this with Polaris. We've also tried it with Lakekeeper. But they use Postgres as a backend, so we can actually sync our metadata into the Polaris metadata, and then we have a REST API. But this is more of a hacky thing. We're still not sure whether this is a viable path, but we are actively working on supporting external REST catalogs. All right, so those were, I think, the chat questions.